well-known theorem of Sperner. So let's remember what this is. So Sperner's theorem says that given a family of subsets of an n-element set, which is an antichain, which means that we don't have two sets, one contained in another. Antichain, so no F properly contained in G. Then the size of such a family is at most the central binomial coefficient. Right, so in particular, if we have a family of sets, I mean, as a particular example, we could take all the sets on the middle level, or any level, and of course there's no containment relation. And if we want to pick the level that's the biggest, then we should take the middle level. And actually, moreover, equality holds if and only if okay, so I'll introduce some notation. So if I write a set here, this means this size subsets of this given ground set. So so for Sperner's theorem, we have equality if either we take all the n-half floor size sets or the n-half ceiling size sets. Right, so if n is even, this is only one family, so this is 2. Okay, and let me mention that probably the simplest way to prove this is a so-called LYM inequality. So I'll mention what that is. So this is due to Lubel, Yamamoto, and Mishalkin, 65. Sperner's theorem is 228. So if F subset Cn is an antichain, then what we can say is that the summation of the sets F in script F of 1 over n choose the size of F is at most 1. And it's pretty easy to see from this that we get the Sperner's theorem because the biggest such binomial coefficient is n choose on half. So if we want to have a lot of things F, we should take a big thing here in the divisor. So we get F is at most n choose on half. So this sort of formula comes up a lot in this topic of bin posets. So let me mention that this thing on the left has sort of two useful interpretations. And it's good to switch between them. So on the one hand, what this formula says is it's the fraction of all the levels we take between 0 and n. So it's a sum of the fraction of the levels we take. On the other hand, you can think of this number as being, suppose I take a random maximal chain. So I take a chain consisting of empty set, singleton, some 2-element set which contains a singleton, and so on, up to everything. So this number is the expectation of the intersection of this maximal chain with the family. This is also easy to see. So it's the expectation of C intersect F across a random maximal chain C. Right. So this will come up a little bit later. Right. So already early on, Sperner's theorem had been generalized. So following theorem is due to Erdős in 45. So now, what if instead of an antichain, what if we have a family with no chain in it of a certain length? So let F contain no k plus 1 chain. So this means family of sets F1 properly contained in F2, and so on up to Fk. This one. So suppose F has no k chain like this. Well, then the size of F is at most, and I'll introduce some more notation here, sigma and k, where all this means is the sum of the k largest binomial coefficients. So it's the sum of, just write this, k largest and choose I. Right, so in the Boolean lattice, the largest level is the middle, and then it gets smaller as we go outward. So if we're k chain free, the best we can do is take the, if we're k plus 1 chain free, the best we can do is take the k largest levels. All right, so Erdős proved this by a nice argument. Let me just, as a warm-up, mention a simple proof of this from the LYM inequality. So if F is k plus 1 chain free, well, we know by like Dilworth's theorem or the dual version Mirsky's theorem, we can write F as a union, F1 union, disjoint union, Fk, such that Fk are antichains, Fi are antichains. Right, this holds in a poset. And if we're an antichain, then of course Sperner's theorem holds. So we have summation F element of Fi. This is for any I. 1 over and choose the size of F is equals 1. But if we just sum this across all of the i's, then we've accounted for all the sets. And since we have k different i's, we'll get a k on the right-hand side. So this implies summation F in the family, 1 over, and choose the size of F is at most k. And now there's something you just have to think about a little bit, that if you're trying to optimize a sum of things, and you want to take add up as many things as you can do, then what you should do is you should add up the smallest things. So this immediately implies that the size of F is at most sigma and k, because we should add up the things of size 1 over n choose n half first, and then 1 over n choose n half plus 1, and so on. Right, so this is Erdős's result. But this LYM inequality came after Erdős proved this thing, so it wasn't so simple back then. All right, so we talked about single relation and chains. So it's kind of a natural generalization of this. So let me introduce a definition. So first let me say, what does it mean for P to be a subposet of Q? So P is a subposet so I'll say this means there's some injection phi mapping P to Q, which preserves relations. So such that x is less than y in P implies phi x is less than phi y in Q. Actually, that's, the poset theorists like Tom Trotter hate this notation because for them a subposet is always induced, so it doesn't mean like this. But so here, so under this definition, for instance, this poset is a subposet of this poset because we can map here, here, here. And every relation we observed in the initial poset, we see in the image poset, so it's subposet. But we'll be also interested in the induced version, so let me say P is an induced subposet. And then I'll just say if there's an injection so that this is this, less if and only if phi x is less than phi q. So for induced subposet, this wouldn't work because here we have a relation which we don't have in the original. Okay, so that's definition of subposet and induced subposet. So Katona and Tarján introduced the following notion. They say that LA and P for a given poset P is the maximum of the size of a set family such that P is not an induced, not a subposet of F. Okay, what do I mean by F? I mean F with the containment relation. So it's the largest family of sets, so that P is not a subposet of F if we think of F as a poset with regard to the containment relation. And of course, F is a subset of the end. And likewise, we also have the induced version of this. So I'll just write a star here, and then I mean induced. So this is kind of a non-uniform Tarján type function. So under this notation, for instance, LAN of a single relation, this is Sperner's theorem, so this is equal to n choose on half. And LAN of, say, a chain of length k plus 1 is equal to sigma k, and so on. All right. So this was in 3. Now let me mention a result already proved back in this first paper. So already Katona and Tarján proved that LA. Okay, actually let me just make it a little bit more general. So LA and P, let me consider actually a family of posets P, and then forbid all of the posets in the family. Yeah, just like in extremal graph theory. So Katona and Tarján considered what happens if I forbid first a V in both directions. So I don't have one set contained in two sets, and I don't have one set containing two different sets, right? And they prove that this is equal to 2 times n minus 1, choose n minus 1 half floor. So this number I wrote here, sometimes this number is n choose n half. So for instance, if n is 4, 4 choose 4 half, that's 6. But 3 choose 1, 3 times 2 is 6. So sometimes it's equal. So for even numbers it's equal, but for odd numbers this is larger. So the proof of this, given a little bit of knowledge, is very simple. So let me just mention it. So Bolabash's theorem about two families says, well, in one interpretation says the following. If we have a family of pairs of sets, so we have a collection of pairs AI, BI, so I equals 1 to m, which satisfies that AI is a subset of BI, and AI is not a subset of Bj for I not equal to j. Then if we sum over the pairs of 1 over n minus size of bi plus ai, choose ai, this number is at most 1. So actually this result, I say the LYM inequality, this was proved in 65, but actually Bolabash proved this thing in about 65, 66. So sometimes people call it the BLYM inequality because this implies that.
Also, normally when you say Bolabash's two-family theorem, it's about intersecting patterns. So maybe you take a complement of BI?
Yeah, precisely. So the usual version is you say that AI intersect BI is empty and AI intersect BJ is not empty. But now, if instead of that, I consider the family of complements of the BIs. Well, what does it mean for AI intersect BI to be empty? It means that AI is contained in BI complement, but BI complement has size minus BI, so. Right, yeah, so that suppose that n is equal to the union AI union. Okay. So this is a consequence of Bolabash's inequality. And what does this give us? So actually, so let me prove an even stronger statement. So let's prove the induced version of this at the same time. So not only is the largest V inverted V free family at most twice n minus 1 choose n minus 1/2, but also if we forbid these only in the induced sense. Now suppose we forbid V and inverted V in the induced sense, then what do the connected components of the poset look like under the containment relation? I mean, we can have these sort of chains, right? If we have a chain of sets like this, then we don't have a V or an inverted V, or we can have isolated elements, but we can't have anything like this because this would immediately be an induced V downward. So the components look something like this. So let me associate to these components, call the bottom set, let that be AI, and the top set, let that be BI. And if we have a singleton component, then let me just write AI equals BI. It's totally allowed in Bolabash's theorem. Right. So what we have is really a sum over sort of chains like this, AI, BI, 1 over n minus size of BI plus AI, choose AI, plus singletons, but in singletons, AI equals BI. So we get 1 over n choose, let's say AI, it's at most 1. But this minus, I can just rewrite this as, put this in parentheses, like this. Now, let's say that we were trying to lower bound this number. Of course, what we should do is we want, if we're going to put a lower bound, we want this thing we're dividing by to be as large as possible, which means that this top part of the binomial coefficient is as large as possible. But bi is not equal to ai, so this occurs if bi is equal to ai plus 1. So we can write the sum over these sort of chains of 1 over n minus 1, choose ai, plus bi, plus sum over the singletons, 1 over n choose ai, is plus 1. But now notice that in both of these things, the best case to do is to take the middle binomial coefficient. Again, if I want a lower bound, I should take ai as close to the center of the n minus 1 lattice as possible. And here is as close to the center of the n lattice as possible. So here I could just write n minus 1 half floor. And here I can write n half. Right. And the other thing is here, I'm just counting one set at a time. But here, as I sum across these things, there's really at least 2 sets from my family being counted. So I really don't want to be summing a 1 here. I want to be summing a 2, because I'm counting 2 sets from my family. So instead of a 1, let me write a 2 up here and a 2 here. And now I'm counting at most the weight of this chain for each term here. And here I'm counting exactly the weight of the singleton, or at most if we say choose that half. So immediately this implies that the total size of f is at most the maximum of n choose n half, and twice n minus 1 choose n minus 1, 2. But this maximum is that. All right, so this was already proved by Katona and Tarján right away. So why do I mention an example where we have 2 different posets going in different directions? Well, it turns out that the situation is a little bit more complicated if we only forbid one of the v's instead of 2 of the v's. So let me mention another theorem from the same paper. Obviously, if I don't write a set notation, I just mean forbid precisely that. Okay. So, let's see. So for time's sake, maybe I don't explain the entire thing, but what is the construction which gives the lower bound for this thing? It's just that we take a code, so we take a distance for a set. So we take, consider the family of n half plus 1 sets. So let's say n is even. So we can write the family of n half plus 1 sets. We can write this as a sort of union from t equals 1 to n of fi, where fi is the family of sets which sum to a certain thing mod n. So this is say x1 to xn plus 1, such that the sum of the xi's is equal to t mod n. And if you think about it, we really can't have 2 different, that if we have 2 different things in this set, which are very close, so which agree on n half elements, then this is impossible. because if we were to have x1 plus xn half plus xn half plus 1 equals some t mod n, and at the same time we were to have x1 plus up to xn half plus xn half plus 1 prime equals t mod n. If we were to have these two things simultaneously, then this would imply that xn half plus 1 is equal to xn half plus 1 prime. So right now what I'm saying is that these sets ft satisfy the property that if I take two sets in ft, the symmetric difference between them is at least 4. And the reason for that is, suppose that it was exactly 2. Well, take two sets in this family of things adding up to t mod n. And the point is that if it was symmetric difference 2, they would agree on all except for one element. But then, by the definition of this set, that means that if we just solve this equation, we get that the last element agrees. So we don't have this. Right? And then the idea is that across these sets, all of these are distance 4 sets, and we have n of them. So we can take one of them of size at least 1 over n fraction of the whole level, because these things partition the sets on the whole level. So one of these FTs is such that FT is at least 1 over n fraction of n choose n half plus 1. Right? Because they're a partition of the level. And then what is our family, going back to the original question of avoiding a V? The family is we take all the sets on size level n half, and then we take these sets on level n half plus 1, which are symmetric difference 4. And the point is that they're too far apart to intersect one level below. Right? So, yeah, so therefore we get the lower bound here of the form 1 plus 1 over n. Now, actually, it's an open question whether this is the optimum for a distance for code or not. So it could be that maybe it's not 1 over n, that this could go up to 2 over n. So it's hard to improve the construction in this way, so we don't know. Okay. And there's one more example of a proof in this area. I want to prove the upper bound here, because this is a method which is used on all sorts of poset problems like this. So let me explain how we get the 1 plus 2 over n times n choose n half as the upper bound for this. So let me switch back to this board. By the way, if there's any questions, feel free to interrupt. Okay, how do we prove 1 plus 2 over n is upper bound? Now remember what I said about this thing on the left-hand side of the OIM inequality, that this has two sort of interpretations. On the one hand, it's the the expectation of a random chain intersecting our family. Right, so summation 1 over n choose f for any family f. This is the expectation of a random chain intersecting f. So of C intersect F. Right. Now, suppose that I take the set C of maximal chains. So this is just the set of all maximal chains. And imagine I partition this into groups. So I write this as C1 union, say, CM, disjoint unions. So I've taken all of the maximal chains and I put them into different groups. Then, of course, this expectation of a random chain is lower bounded by the largest across all of these groups of the expectation of a random chain hitting F. Right? Because I've just concentrated the probability space to where there's a higher expectation. So this is less than or equal to, if it's not clear, I can show in more detail, but at most, the expectation of a random C from Ci of the size of the family intersect C. Right? So of course, if I have some very likely part of the chains in terms of intersecting F, then that's an upper bound for the overall expectation. And we saw that the overall expectation is this sum of 1 over n choose F. Right? So now I just want to mention this is the idea of really it's Grigsley and Liu. This is the so-called partition method. So using this, we can immediately get this 1 plus over n upper bound for this specific question about the V. What is the idea? Maybe just to be safe, let me write a plus big O 1 over n squared. So we don't have to worry about lower order stuff. So imagine I have a V-free family. Let's say C tilde is the set of those chains which hits the minimal set in my family. So this is the set of C such that C hits minimal set in F, inclusion minimal. So F is V-free. So on the one hand, I have those chains that hit the minimal element of F, and then on the other hand, I have those sets which don't. So this is set of all chains minus the set of chains which hit the minimal set. Now, if I forbid a V, I'm definitely also forbidding this chain of length 3. Because as we saw, the V is a subposet of this chain, right? So I don't have a chain of length 3. So what happens with those chains which miss a minimal element of my set? Well, they can hit at most one element of my set. Because I can have at most 3 elements in a chain. So if C is not a chain which hits a minimal element of my family, then this implies that the intersection of this chain with my family is at most 1. Right? Because I don't have this. On the other hand, suppose C is a minimal chain. Now, let me make one more remark that in the Boolean lattice, we have a lot of concentration towards the middle. So, in particular, the number of sets which are bounded away from the middle is totally negligible. So, the number of F such that the gap from F to the middle is, say, greater than, I think it's something like cube root of n log n. Maybe it's square root, I forget. Square root. The number of sets like this is actually it's little o 1 over n, n choose n. So tiny. So if I'm not worried about the 1 over n squared term, I can forget about all of these sets which are far from the middle. But now, let's look at a chain which hits a minimal set in my family. So So my whole family lies close to n². And if I consider a maximal chain, which hits this minimal set for my family, how many other sets can it hit? Well, it can hit at most one other set. But if we look at the level right above this set where it hits, here we have roughly n½ sets. Because this minimal set is roughly n², the number of supersets of size 1 bigger is roughly n². So the number of these sets is approximately n². And of course, only one of these sets can be occupied by the family, because if it was 2, it would have a V. So at most, one of these can be occupied. Yes, it may not be the one right above, but it only gets better if it turns out it's some higher up set. So suppose it's right above. Well, then what's the probability that this random chain hits this set also? Well, it's like 1 over n², which is 2 over n. So in this case, we can write that the expectation of f intersect c across c in this minimal family is at most 1 plus 1 over n. Okay, sorry, 1 plus 2 over n. Because 2 over n fraction of the chains hit 2 sets from the family at first. All right. So I mentioned this because this is the fundamental idea for proving a lot of things in this area. Sometimes it's much more complicated than this, but this is the basic idea. All right. So all this was about this first paper of Katona and Tarján. So let me mention some other things. Yeah. No. So there's no improvement to the upper bound. And the lower bound, there's 2 ways you can improve the lower bound. One way, you could find some better code, which is a hard problem in coding theory, potentially, to improve this 1 over n bound. And the other is to find some very different construction that doesn't involve a code. And so far, this has not been done. So this is the record still. And actually, since I promised open questions, let me mention that. So suppose instead of a V, suppose that we wanted to forbid two sets A and B, which intersect at precisely C. So we forbid A intersect B equals C. So suppose we forbid this. Now, this lower bound construction with the code is still valid, but the upper bound proof is no longer a valid proof. And the best upper bound, which is known for this case, is of the form 1 plus C over root n times n choose n². This is due to Klein. So for this question of instead of forbidding the V, forbidding an intersection, the problem is still open. I don't know. Probably the answer is C over n, but the current vector is C over root n. All right, let's move on. All right, so since this initial result, many other things have been done. So, for example, consider this poset. They call this the butterfly poset. And the funny thing about this poset is that if we look at the Boolean lattice and we take 2 consecutive levels, we don't find this poset. This you can think about a little bit. I mean, of course, if we take 2 things, they have a unique union 1 level above, so we can't have 2 different terms because we have a lattice essentially. Right? So actually, so the bonus Katona and the swimming pool prove that this is equal to this. So we can take the 2 middle levels as we can do. And maybe I won't go through the details, but the basic idea is that, well, actually this poset we have to have a bound of this form. Why is that? Because this butterfly poset is a subposet of both this upward y, because we could send the top two elements to the top of the y and the bottom ones to the bottom, and the downward y for the same reason. So we have this upper bound, and then it was proved that in fact this is at most this. And again, there's a very simple proof using this chain partitioning argument, which I won't go through. Or maybe I will. I mean, the point is that if we take again, we don't have a 4-chain in such a family, so if we take a sort of middle level set and we take a chain through it, well, we can have an element on one side, but on the other side we don't have many. So again, we can do this kind of thing and get a bound. Okay. So since then, many other posets were considered. In the case of a general poset, very few things are known, but there's a very nice result of Boris Buch. So theorem due to Buch. If we take any poset whose Hasse diagram is a tree, then we know asymptotically how large this extremal number can be. The extremal number is asymptotically the height of the tree minus 1 times inches and a half. And the idea is, of course, if we forbid a tree of a certain height, we can take those levels, this many consecutive levels, because we don't have a long enough chain to create a T. But in fact, the upper bound also holds. This is what Buch showed. Yeah. And so, yes, this is known in many other specific trees. So let me mention some other exact results. So with Abhishek, we proved that if you forbid a y, so a y means a chain followed by exactly 2 elements above at the top, where this chain has length k, and simultaneously forbid the opposite y, so a chain of length k with 2 elements right below it, then this number is sigma nk. So this is a generalization of this thing. And in fact, it's interesting that actually, even if you forbid only in an induced sense, we still have the same bound. So I proved with Yao Wang, and it was independently proved by Ryan Martin, Bishek, Walker. But actually, LA induced version of n of yk in both directions is also the same. Yep. And actually, these two proofs are very different, and they have different generalizations actually. So this proof has a nice generalization that instead of induced version, we can consider a stronger property where actually we restrict these two sets to lie on the same level, and you can prove the same bound. Whereas the proof we proved here actually generalizes to the lattice of vector spaces. So you can prove the same bound if instead of considering subsets, we consider vector spaces. So they're very different. All right.
When you say vector spaces, is that Subspace relation?
Right, so subspace formation. So we start with the finite field, FQ, and we look at FQ to the n, and you get the lattice of subspaces under subspace relation. The question is the same. So Sperner's theorem, for example, is the same. So let me mention, along this line, let me mention one. I see I forgot to mention what is the construction for LA and the two V's. So again, I mentioned that this number is equal to 2 times n minus 1 to the n minus 1 half floor. I didn't mention what the construction is. What the construction is, we just take an n minus 1 element ground set. And we take the middle level, that n minus 1 element ground set. And then we take every set here plus the element n. So each set here, let's call a set here A union n. Right? So if we do this, essentially we have a matching between these two levels. Is it clear? So we take all the middle levels of n minus 1 element set, and then we have one special element, which we then add back to all the elements. So we get essentially 2 copies of this middle level, but they're paired up in a matching form, so we don't have any V in either direction. So this is the optimal construction. Okay. Now let me mention, first, taking this construction, a generalization, an idea. So this is a conjecture, new conjecture. So LA N. And now I say if instead of a V and inverted V, we forbid 2 binary trees. I give the case when the height is 3, but it has an obvious generalization. So consider 2 binary trees in the opposite direction. I say that this extremal number should be equal to twice sigma n minus 1, 2. So this number is equal to twice sigma n minus 1, 1, right? So here I say we should take the 2 biggest levels of the n minus 1 lattice. And the construction is as follows. We just take, here's the n minus 1 lattice. And now we take the middle 2 levels. Okay. And now we take these, in addition to taking the middle 2 levels here, we take the middle 2 levels plus the special element n. So we get 2 more levels here. So each set here, call this A. This is A plus the special element n. Now between this and this, we have a matching. Because the sets here are just the sets here plus n. And likewise, between here and here, we have a matching. Right? Now, how much of the binary tree do we have? In terms of the binary tree, we can start with a set here. We could go up in this direction, and we can go up in this direction. And going up to the right, we have plenty of sets to continue to. So we have at least 2 more sets containing this, because this is a complete 2 levels. But when we went up to the left, we only have 1 more set to continue to. So if you think about it, this construction is, we're exactly missing the binary tree by 1 set in both directions. So I think that probably this is true, and this has an obvious generalization if we have a binary tree of height k to taking k levels. And so this is a new conjecture. And let me mention one very old conjecture. It's old, but due to Katona and Tarján. So the conjecture of Katona and Tarján. LA and let's forbid a V of size 3 going up and a V of size 2 going down. Okay. So they conjecture that this is equal to 3 times n minus 2 over 2 floor plus n minus 2 n height. Construction. Same idea, but now take two special elements. So take n minus 1 and n, put them aside. And now in the n minus 2 lattice, so starting with the n minus 2 element ground set, consider the middle level. But don't take the middle level. Just use the middle level and add one or both of the special elements to it. So we get, actually maybe let me write it. How is it? So add one or both of the special elements to it. So what we get is a bunch of V's going downward. Because we either add the element n minus 1, or we add the element n, or we add both n minus 1 and n. And we take a bunch of V's. Right. And then to flesh out the family, we take all those sets on level n half, which contain neither of the two special elements. Sorry, we add all the sets on the lower level, which contain neither of the two special elements. And the point is that because these sets have the two special elements, and these sets are one size smaller, they can't possibly be contained, because these sets have two elements which are not part of these sets. So that's the construction. So this is still open, no progress since the original paper. All right. So LANP has been determined for many families, but there's a conjecture by Katona and Griggs that given a poset P, consider how many levels of the Boolean lattice we can take without P. So take as many levels as we can take with no P. So no matter how large n is, we have no P on this many levels. So call this number E of P. This is the maximum number of levels we can take. So the conjecture due to Griggs Katona is that basically for any poset P, the correct construction is to take as many levels in the middle as we can. And it, of course, it's not true, as we saw with the V, that we should take these codes and things like this. But I just mean the first term, so the leading asymptotic. In other words, what they conjecture is that for all P, LA and P over n choose n half tends to E of P as n goes to infinity. This is their conjecture. Okay, so E of P is equal to the maximum number of levels, consecutive levels, in Cn with no P.
So E is dependent on
No.
the way you write it there.
It's for all n. What? No matter how large n is, we don't have P in E of P consecutive levels. Right? So that's what E of P means. So for instance, E of this poset, which I mentioned before, this butterfly poset, this is equal to 2, because it's never in two consecutive levels. But if we actually went a little bit further, this poset is equal to 1, because two consecutive levels do have a thing like this. And so on. So this is a conjecture. It's totally impossible conjecture. Why is it totally impossible? Because well, it's not false, maybe, but already for the diamond. So for this poset with one set containing two sets containing one more set, we don't know what the answer is. So E of this diamond poset is equal to 2. So the conjecture should say that this is roughly 2 times n choose n half. But there was a sequence of bounds. So a trivial bound is 3 because we don't have a 4 chain. It was improved to 2.9 roughly by Grigsley and Liu. It was improved to 2.8 by Axenovich, Mansky, and Martin. It was improved again to 2.7 by Grigsley and Liu. It was improved to 2.5 by Kramer, Martin, and Young times n choose n half. And then finally, with Abhishek and Danny Gross, we were able to prove 2.207 times n choose n half. But this is still an open problem. So there's a huge gap between the constant that's known and 2. All right. So that's that. And let me mention another. Let me just mention a very great weakening of this conjecture. Can we even prove that LANP is bounded by some function of E of P times n choose n half? So can we prove that LANP is at most, say, 100 E of P to the power of 100 times n choose n half? Sorry, that's LANP. Can we prove a bound like that? And even this is open. So even proving some constant depending on E of P is an open question. Right? So I will mention that if E of P happens to equal 2, this is true. So suppose that E of P equals 2. Well, what does this mean? This means that P is eventually a subposet of 2 levels for some m. So some ground Boolean lattice, P is a subposet of 2 levels eventually. Right. Okay, sorry, right. So it's true for E of P equals 1. So if E of P equals 1, that means that P is eventually contained in 2 consecutive levels. But 2 consecutive levels is always contained in a sort of spidery tree like this. A tree of the form where we put a middle subdivision for text to relate all the things. But then by this theorem of Boris-Buch, which I mentioned, for a tree, we have a bound already of the height of the tree, which is 3 minus 1, which is 2. So a bound of n choose n half. So it's true for E of P equals 1, but for larger P, it's for larger E of P, it's not known. So I'll leave that open. And in my remaining minute, let me just mention that, so there's many results for the Boolean lattice. Recently, we started looking more at the linear lattice. This was mainly initiated by, let me get his name right, Shariari and Lee. So instead of looking at the lattice of subsets, we look at the lattice of vector spaces. And here, many things carry over. But the one interesting fact that I want to leave you with is that in the lattice of subspaces, we have much more concentration towards the middle than in the lattice of subsets. So, for instance, Sperner's theorem is sort of unique in that it's the only forbidden poset where really n choose n half is the answer. But for vector spaces, it's not true. So for the vector space version, even if you forbid some of these V's and inverted V type posets, so let's say L and Q in this way, even forbidding these things, sometimes we get the same answer as in Sperner's theorem. We get the answer n choose n half. So if I had more time, what I would mention is some proofs of this, but I think we're out. But let me leave you with that for For the vector space version, it's interesting. It'd be interesting to classify precisely what collections of posets actually we get the same as Sperner's theorem, which is because that's all. So I'm going to stop there.
Questions? For your conjecture, the like two binary tree of.
Yep.
So asymptotically, this
It's true.
is true by Boris's theorem.
Yep.
Even if you have two trees.
Yeah. It's enough to forbid one, and it's true asymptotically about both.
Okay.
So this is an exact conjecture.
Right.
Yeah, so today I talked mostly about exact things because usually people talk about asymptotics, about posets, so I wanted to mention some examples also.
And for the last conjecture, when you replace it by induced version, then is it false or is it?
It's not known either. It's conjectured also for the induced version that this should be true. But again, the point of me mentioning the diamond thing is that this conjecture is not verified even for the diamond, which is this very simple poset. So the Griggs-Katona conjecture is very, very, very difficult because the diamond is already very, very difficult. But my hope is that maybe we can prove a weaker conjecture of just proving a function of ERP rather than proving that. But this is also a seemingly very hard question.
Any other questions? So if not, let's thank the.